Thank you very much for the invitation. It is a very wonderful invitation. I'm very glad to be here. And so, during the introduction, I will speak about microscopy, spectroscopy, and microscopy using coherent Raman, which is a Raman spectroscopy employing ultra-short laser pulses, and some applications mainly in the bioimaging realm. So first of all, one of the most important slides is funding on this one and the people here. Without them, nothing of what I will present you today would be possible, of course. This is the list of what I would like to talk today. I will start from the motivation. So why you need Raman, and in particular coherent Raman. And then I will introduce Raman in the standard implementation, which is spontaneous Raman, and in the coherent version. And then a few applications. Let's see how much time I have. I managed to go through all of them. Yeah. Yes. Okay. So let's start from the motivation, which is to overcome the limits of fluorescence. Fluorescence, in 99% of the cases, is wonderful, can be employed in many scenarios. You can produce very nice images like this one. But so fluorescence, either in the standard one photon or, as we heard previously with Gilberto, with two photon fluorescence, you can visualize morphological details in many samples, like in cells and tissues. Typically, fluorescence employs either exogenous or endogenous markers, and it can be employed with a very high speed, high sensitivity, down to the single molecule level. But there is a problem, which is the following. Sometimes you cannot add exogenous fluorophores, you cannot add these chemicals because they might perturb the system. So what you see is not what in reality happens in the cell, because this heavy burden of the fluorescent molecule could be perturbing your system. Sometimes these fluorophores are phototoxic. You can generate maybe reactive chemical species like reactive singlet oxygen states, which might oxidize or perturb your system. And then you have also the color barrier that I will show you in a minute. And so the solution is to have a different contrast mechanism using some endogenous contrast mechanisms, intrinsic and level. Okay. So this is what I was mentioning, the color barrier, in the sense that if you want to image a multicolor like this one, okay, you see here, these are three colors, red, green, and blue. You can do 3, 4, maybe 5, but then you hit the color barrier. This is a series of fluorophores. You see the absorption and the emission 1, 2, 3, 4, 5, 6. And you see that in the visible, these 6 fluorophores, they overlap. So the emission of one overlaps with the absorption of the other. And so it's hard to separate the signals. So the solution comes with vibrational microscopy. Vibrational microscopy is a technique in which you can identify the molecules inside your sample, biological sample or any other kind of sample of interest, because any molecule will have a certain vibrational spectrum, which it can be used like a fingerprint to uniquely identify the chemical species of interest. This is non-invasive, so you don't need to add any staining or labeling. This is a typical spectrum. You have 2 regions. Typically, one is called the fingerprint on the low axis on the left. So this is the Raman shift. So this is a vibration in the wave numbers, inverse centimeters. If you multiply by the speed of light, this becomes a frequency. So this is low frequency. This is high frequency. In the high frequency, you have typically the hydrogen oscillation, because it's the lightest atom, of course. So you typically have in proteins, lipids, so the stretching of the hydrogen bond with C, or also water here. You have a kind of useless silent region, and then you have the fingerprint, in which you have a lot of information. So in standard implementations, you can either go in direct absorption in the infrared through the absorption of light in the infrared. But if you want to have a better resolution, a better penetration of light, you can do Raman. And for detecting any vibration of a certain, say, capital omega frequency. So if this is the energy, this is H bar capital omega, you go with typically infrared light. So this is not an absorption, this is a virtual level. 1 every 10 to the 7 photons gets inelastically scattered, and so you have a Stokes photon out, and the frequency difference between the pump and the Stokes matches your vibration of interest, capital omega, which is this horizontal axis. So if you plot the photon energy as a function of the Raman shift, you get this spectrum. Nice. So now, why would you like to go from spontaneous Raman, which is now, commercially available and employed in many labs, to coherent Raman? Well, in spontaneous Raman, you have the following. So this is the beam waste of the laser. Okay, you typically need a CW continuous wave laser, and you have a certain molecule that you want to observe, whose frequency of oscillation is capital omega. So you see that all these oscillations occur in a kind of random way. So these are thermally active vibrations because every molecule oscillates with their own random phase. Now, in coherent Raman, you do the following. Of course, it's more complex because now you need not one but two lasers, and not CW but pulsed. So you see you have a pulse, which is pump, and the pulse, which is called Stokes. But now, what you do is the following. You see that you have a coherent molecular vibration. So all these molecules oscillate in phase because the oscillation is driven by your optical fields, which are pulling and pushing the molecule. So if the molecule has a certain capital omega oscillation, it will go in resonance and will oscillate. If there is no resonance, they will not oscillate, full stop. Okay? So you see that you have a much higher signal. Typically, you have 5-6 orders of magnitude faster imaging because you have a higher signal output. And so you go from about a second measurement time to microsecond measurement time. And so now you can do not only a spectrum, but you can do an image in a few seconds. So a high resolution image with 1,000 by 1,000 pixels would take 1,000,000 seconds on the left. Here, if you go to microsecond, you can do the entire image in a second. Now, there is a problem of coherent Raman, super fast, but it is inherently single frequency. What I mean is that now, if you have a second molecule oscillating at another frequency, say capital omega prime, no problem. It will also provide your signal. On the right, it will not oscillate because it will not fulfill anymore this resonance condition omega pump minus omega Stokes. Okay, so in standard implementations, coherent Raman is super fast but single frequency in nature. So in our lab, we pushed in the last 5-10 years the technology towards broadband coherent Raman in order to retrieve the entire spectrum of spontaneous Raman, keeping the high-speed nature of coherent. In the coherent Raman, you typically have two possible implementations. 99% of the times. There are also other more exotic ways, but most of the people do either CARS or SRS. CARS is more famous because it was invented and developed a bit earlier. Nowadays, more than 90% of the people are turning into SRS. Well, you always have both of them at the same time because the input in both cases, you need a narrowband pump and a narrowband Stokes, okay, whose frequency difference matches the capital omega vibration of interest. So the laser input is the same. The difference is how you detect the signal output. So in the first case, you just have up and down. Once you have an interaction with the pump and the Stokes field, and what you measure is the annihilation of the pump. So you have a stimulated Raman loss, or the formation, the amplification of the Stokes, which is called the stimulated Raman gain. Of course, this is not in scale. This gain or loss is a part in a million. Okay, super small. And so you typically need lock-in amplifiers and modulation transfer techniques. In CARS, you go up and down another time, so you have an extra interaction with the pump, and then you generate now a new color. This anti-Stokes is in the blue, so it's easier to detect. You just filter out the colors, and you count photons. Again, this is not in scale. The number of photons here in the anti-Stokes is going to be 1,000,000 times less, but no problem. You need a spectrometer or a photomultiplier tube, and you detect it, no problem. But CARS has other problems that I will show you later. Okay, so you always have both of them, and depending on how you measure, you detect either SRS or CARS. I will show you both examples. So to sum up, spontaneous Raman, very high information content, low imaging speed. standard coherent Raman, high imaging speed but low information content, and we try to push, okay, the technology towards this up right corner. How can you do that? How can you turn coherent Raman into broadband and not anymore single color? Well, you can do it because you can, well, first the stupid idea is tuning, okay? So if you tune either the pump or the spokes, it's the same. You create a larger or narrower gap, and so this capital omega becomes larger or smaller, and so you also shift the anti-Stokes generated photons, no problem. And so you tune, you do, for example, one image of your sample at one Raman shift, then you tune to a second, a third, a fourth, and then you build up a hypertune. Another way to go in this upright corner is shown in the following. So how can you do this? Well, you can, for example, replace a narrowband pulse into a broadband pulse. Now, instead of having 2 picosecond pulses, you have 1 picosecond and 1 femtosecond pulse. It can be either the pump or the Stokes, but typically you prefer the Stokes because of some limitations in the cars. And now you need to generate broadband light. So this is one example in our lab in which you have infrared light. Here you don't see it. You focus it in a piece of glass, and at the output you have a rainbow of colors. In this case, you see the visible, this red, green, yellow color, but in this case we were using the infrared that you can see by eye. And then at the output, what do you do? Well, for SRS, you have these broadband Stokes here. And so this broadband Stokes allows you to measure in parallel all the molecular vibrations of interest, capital omega 1, 2, 3, okay? So here, this broadband pulse, this broadband spectrum, will have on top some tiny peaks. Again, these peaks are a part in a million, so very small. And so what would you like to have? You need now a spectrometer capable of measuring millions of spectra per second, because you typically employ megahertz repetition rate lasers, modulated at megahertz repetition rate, because you need to be very quiet, so high frequency modulation to get low noise. So you need a spectrometer with capable of measuring millions of spectra per second at the sensitivity which is a part in a million, okay? And this is not commercially available. Spectrometers nowadays can measure a few thousand spectra per second, and with the digitalization of 8, 12 bits, it's hard to measure a part in a million. So that's the technological burden that we had to solve in the recent years. Another way is the cars. So in cars, now if you have these broadband Stokes, you go up and down, you populate these oscillations, and then you go up again with a narrowband pump, and then you generate all the colors in the anti-Stokes. And so here, instead of one peak, you have all these peaks at omega 1, omega 2, omega 3. And this is easier in the sense that you have just a spectrometer, but you have to fight against a signal, a spurious signal that you don't want, which is called the non-resonant background, that I will show you in a minute. These are a few images of microscopes that we built in our labs in the recent years, just to show you, give you a hint of what we do. We typically prefer to build microscopes because it's easier than buying commercial microscopes and modify them, because you need to modify them too much. And so it's better to have an open air setup in which you can replace and put your hands inside and do what you do. Okay? People ask me, are they upright or inverted microscopes? Well, yes and no, in the sense that most of the times these are transmission microscopes. So we measure thin samples, typically single cell single cells on a dish, or biopsies, thin biopsies of a few microns, and so we go in transmission. And so these are sometimes light goes from top to bottom, like in this case, sometimes from the bottom to the top, like in this case. Okay, so let's come to a few examples. Let me check what time it is. And yes, okay. The first one is broadband cars, and then we'll go to broadband SRS. So I'll give you a couple of examples of both techniques. So in broadband cars, we do the following. I already presented you this, okay, which is called multiplex cars, and in the standard scheme, this is also called two-color mechanism. two color because you have pump Stokes, pump anti-Stokes, and there's no problem. But there is also another possible mechanism, which is called three-color cars. In the three-color cars, you do the following. Okay, this is the ground state. These are the oscillations. You can have the first two interactions with the broadband beam. Okay, this, as you see, allows you to reach also another oscillation at this omega-4, which is at low frequency, so towards the fingerprint, which is the most informative but also the most difficult region because the signals are rather poor in intensities. To reach this omega-4, together with omega-1, omega-2, omega-3, what do? Well, you have a broadband Stokes pulse, so this one. So instead of having pump Stokes, you now select two photons out of this rainbow of colors. So you have now several possible combinations that you employ all together. In the frequency domain, you take a couple of colors. In the time domain, you can think of it as in this way. So you have now a very long in time pump because it has narrow band spectrum, and then you have a very short Stokes in time because it is very broadband. So this is picosecond, this is femtosecond. Of course, you need to compress and check your phase, spectral phase, because you need this short pulse duration at the sample plane. So you go through many optics and objectives, so you have to take care of the dispersion. But it's possible. And now, if you have this Stokes, which is very short in time, in the time domain, you can think of it as a hammer that hits the molecule. So if you hit the molecule with a hammer, very sharp, very short in time, the molecule will start to oscillate. Okay, you have to kick it with a kick which is shorter in duration than the period of oscillation of the system itself. No? Like a pendulum. If you gently push it and you go away, it will not oscillate. If you hit it, it will start to oscillate. Okay, so your pulse duration must be shorter than the duration of the oscillations that you are interested in. And so you need very short pulses in the order of a few femtoseconds. In our case, the short pulse is our hammer. So the two interactions with the Stokes will hit the molecule, which is the hammer. Now the pump, which is now narrow band, will do the rest, and you generate now these new Carser photons, which tell you which are the resonance conditions of your cell. Okay. In our case, we have about sub 20 femtosecond pulses at the sample plane, very close to the 16 femtoseconds transfer limit duration of the pulses. And this is verified in the following, because we can measure the upper limit of the Raman signals, and by just converting the frequency into time, we know the frequency. Okay, we know the duration. Okay, so I skip a bit some details and we go to the results. There is also some data analysis tools with deep learning, and these are typical results. We start from plastic samples, artificial samples to test the performances, and these are polystyrene beads and plexiglass beads immersed into a solvent, which is the MSO, and we can discriminate the chemicals. These are all transparent samples by telling the spectrum of interest. So this is the spectrum in the fingerprint of the different components. And then we can also image cells, like in this case, these are hepatic cancer cells. We can distinguish the nuclei blue. We can distinguish the lipids and proteins in red and in green, because they have different spectra. So they have different resonances, different oscillations. We can do tissues. This is a mouse model in which you identify, so this is the HNE stained sample in which the histopathologist says that here there is a tumor. I'm not an expert, I cannot tell. We take the next adjacent slice, which is not stained, which is just white, and with cars we can distinguish the tumor area in red, the healthy tissue in green. We can also see the collagen in blue, and we can see where the tumor is. Here you see where red is denser, means that the tumor is more severe, and you can see a gradient toward the green. Just quickly, let's see how much time I have. We go to broadband SRS, 2 minutes, okay? In broadband SRS, the problem, as I told you, is how to measure megahertz spectra at 10 to the minus 4, 10 to the minus 5 sensitivity. Well, we built a multi-channel lock-in amplifier on chip. These are 8 boards, and each board contains 4 lock-in amplifiers. This is done with the CMOS technology. And we can now measure discrete spectra in parallel. These are test results in different solvents. We can distinguish different chemical components doing imaging. And we can also do biology. For example, this is a fibrosarcoma injected under the skin of a mouse. And then there is one slice which is stained with H&E. The next adjacent slice, which is not colored, is measured with level-free SRS. These are 3 images at 3 Raman shifts, but we have more than that. We have 32 channels. So if we plot the average spectrum of the cancer area, the healthy tissue, we can do a multivariate curve resolution analysis to distinguish the cancer here in red associated with this spectrum and the healthy tissue here in green associated with this spectrum. So we can identify the tumor regions with respect to the healthy regions in an unsupervised manner. This is now also becoming a commercial product. I'm not part of this spin-off company, but many previous PhD students of mine are now working with this company, which is called Cambridge German Imaging, but is based in Milan, in Politecnico di Milano Polli Hub Startup Accelerator. And so they have this multi-channel lock-in amplifier, and they have also a full microscope system that they are selling with the laser, the microscope, the detection chain, and everything. And they can perform H&E, let's say, comparison of H&E stained with AI stained tissue, and they are very, very similar, almost identical one. Okay, so I think maybe I skipped the very last slide. And I thank you very much for your attention. And I mentioned that you can come working with us in the framework of either Laser Lab Europe, which is an access facility that provides access to our labs, or the IFOX Integrated Infrastructure Initiative that we are also part of. Thank you very much for your attention.